Hi, and welcome to Module 4 of Lecture 10. This is the first of a series of modules covering matrices. There's a list of names here on the screen right now. We'll get to that in a second, but first let's discuss sort of the broad strokes. What is a matrix? Well, a matrix is just a collection of scalars put in some coherent order. So this over here is a matrix. This is a 2 by 2 matrix. There are different kinds of matrices, as we'll see. It has 4 elements in it. All the same terminology we dealt with before for vectors is still true. This matrix has 4 elements. We generally refer to a matrix as a capital letter. Sometimes the dimensions of the matrix are listed as a subscript. So this would be a 2 by 2 matrix. In general, we can write an n by m matrix, where the first dimension is the number of rows. Each one of these is a row, in the common normal English usage of the word row. And each one of these is a column, and the m refers to the number of columns. So if I had this matrix instead, I would have a matrix that had 3 rows and 2 columns. Or if I had this matrix, I would have a matrix that had 2 rows and 4 columns. Any combination of rows and columns is fine. We'll deal with the definitions of the various types of matrices shortly. But point is, you could have any number of rows and columns, and they're all fine. You can view these things as a set of row vectors plopped down on top of each other. So for instance, this would be one row vector, this is another row vector. So this matrix right here would be the row vector 1, 8, 5, 4, and the row vector 2, 1, 18, 2. So there's 2 row vectors put down on top of each other. More common is to view this as a bunch of column vectors placed close to each other. So there's 1, 2, 5, 1, 8, 18, and 4, 2. That'd be 4 column vectors squished together. That's more common because of its connection to data, which we'll get to very shortly. But the point is, all the same ideas hold. Each element of these matrices is denoted Aij. Aij is the element in the ith row and the jth column. Same notation you have for vectors. Instead of having 1 subscript, you have 2. So for instance, in this matrix right next to this, A22 equals 4. It's the element in the second row, second column, whereas A12 equals 3. It's the element in the first row, second column. Now you sort of see why I said a few modules ago that a lot of this is going to involve just sort of keeping track of where things are. A lot of dealing with matrices just involves trying to figure out exactly where all the elements are and make sure you deal with the elements in the correct spot when you're multiplying or adding or whatever. There you go. So that is that's an element, same meaning for vectors. And in fact, matrices are sort of a broader, in some senses, a broader category compared to vectors. If you have a matrix, let me clear this off. If you have a matrix like this, it has 1 row and 2 columns, that's a row vector. And if you had a matrix like this that had 2 rows and 1 column, that's a column vector. A 1 by 1 matrix is just a scalar. So that's it. I have parentheses around the outside. It's nothing really a big deal about that. I can also have square brackets on the outside. Still a matrix. Right, a matrix is just a collection of numbers. Now, why do we use them? Before I get to these definitions, they're used for different purposes. In statistics, they're often used to represent your independent variables, the data for your independent variables. And there, that's when you view this whole thing as just a series of column vectors stuck together. So we talked about before how you could view one one variable, the data for one variable, as a column vector with all the data points in it. It's a length n corresponding to n different elements for n data points, so on. Well, if I had a second variable, I could do this, 6, 5, 1, 3, and so on. Well, if I shove them all together, I get a matrix. This matrix is usually called X for the independent variable X. And here, this would be a matrix corresponding to 2 variables with 4 data points each. And you could write them all together. And you would use this data matrix in your analysis, in your regression analysis. So this comes up a lot in statistics when you're dealing with calculations, and we'll in fact do an example of this later in the lecture, in a later module. So that's also something that comes up a lot. And here's where you'll probably see it most often. The other thing you'll see quite often are matrices used for some kind of theory purpose, usually as a linear operation. It'll turn out, and we'll talk about it a little more in a later, I think next lecture. It'll turn out you can represent a linear operation in terms of a matrix. This is especially common when dealing with Markov chains, Markov processes, where your behavior in the next period depends on your behavior in this period. Well, the transition matrix, the transition function between 2 states, so where you are now versus where you are next period, when you have a finite number of states, can be represented by a matrix. So that you call it a transition matrix, and it takes you from one place to another. This is a topic we're going to cover in the lecture after the next lecture, so lecture 12. There'll be a few modules on Markov processes and how to use matrices to compute steady states and to figure out where the process goes over time as you keep applying this transition matrix to your state vector, it's called. This stuff is very relevant both in understanding Markov chain Monte Carlo when you're doing statistics and trying to simulate your posterior distributions and things like that. It's also very useful if you're doing any kind of modeling that involves either explicit Markov processes, such as explicit Markov processes, which come up a lot in models of boundary rationality when you're trying to define transitions between states that are not necessarily due to rational maximizing behavior. So this stuff comes up a lot in those contexts. You also see these matrices when you're trying to understand properties of a system, like for instance, what's the sort of characteristic vectors? What are the vectors that sort of stay the same when you apply this matrix? This has relevance to things like time series, also for things like analyzing network structure. We'll discuss that also in lecture 12 and looking at eigenvalues and eigenvectors, which are related to these matrices and the properties of the matrices, where the matrices correspond to some system, some process. So again, we'll deal with all this later, but these are ways in which matrices come up in political science. They're also often a way of representing a system of equations. We'll see how to do that more in the next lecture as well. Next lecture as opposed to the next lecture after that. But that also uses matrices. Okay, so that covers the basics of what a matrix is and why we use them, and most of the notation. Again, there's not much notation to a matrix. Note that when we have an element, Aij, the I and the j correspond to a telling you where the element is, whereas the subscripts of the matrix itself tell you how big the matrix is. So that can be a little tricky, but again, there's a times in this one, n times m, n by m, we say, n by m, sorry. Whereas over here we just say Aij, so even in speech it's distinguished a little more. So that's the broad strokes. Now, why did I put all these terms on the board? Well, the rest of what we're going to talk about in this module are special kinds of matrices that come up a lot. So the first one is a square matrix. A square matrix has the same number of rows and columns. That is all a square matrix is. We care about that because it turns out a lot of the stuff you want to do with matrices like inversion or taking determinants require square matrices, the same number of rows and columns. So they're a very common type of matrix, and you'll see them quite often, but again, all it means is they're the same number of rows and columns. This is a square matrix. This is not a square matrix, so not square, square. That's it, there's nothing else to that at all. Okay. The zero matrix is typically a square matrix, but I don't think it has to be, with zeros everywhere. Not used that often, frankly. If you add a zero matrix to any other matrix, you get the matrix back again, which is why it exists. Isometry has to be square. Anyway, that's a zero matrix. Much more commonly observed is a diagonal matrix. A diagonal matrix has elements only along the diagonal. So if you have a square matrix like this, then this is a diagonal matrix, and there's nothing anywhere else. If there's something somewhere else, it's not a diagonal matrix. So that's a diagonal matrix, and they're best defined for square matrices. You could think of a matrix that's not square, you could define it for in theory, but pretty much always you see diagonal matrix defined for, a diagonal matrix would be square. Pretty much always. If all diagonal elements are actually 1, you have what's known as the identity matrix. This comes up very often, so it has its own actual symbol, I, and you see either IN or IN by N, noting that it's always square. This is the identity matrix. As we'll see in a later module, when you multiply the identity matrix times any other matrix, you get back the original, you get back that matrix. So I times A gives you A. So it's going to be pretty useful and come up pretty often. That's the identity matrix. It serves the same purpose as a 1 in just normal algebra. A 1 scalar, right? A 1 real number, which multiplied by any other real number gives you back that real number. It's the identity. It's a multiplicative identity. Unlike vector multiplication, I shouldn't say that. Matrix multiple. Anyway, forget that. We'll get to that in a second. Okay. So that's that. Lower or upper triangular matrices have elements only below the diagonal or above the diagonal, including the diagonal. So this is a lower triangular matrix. And by the way, I'm writing 3 by 3s for no particular reason. You could write 5 by 5s or 2 by 2s or whatever. There is a lower triangular matrix, so-called, looks like a triangle. An upper triangular matrix, you can guess what happened there. I'll just put them up here instead, save myself a thought. That is an upper triangular matrix because the triangle occurs above the diagonal. So that's an upper triangular matrix. A submatrix over here is what you get when you remove a row and column from a matrix. So if here's my matrix, I'm just going to make this general this time. I should use 2 by 2. I guess I can't use 2 by 2 for this case. It's not very interesting. 2, 1. Sorry, no, 1, 2. Apologies. 1, 3. A 2, 2. A 2, 3. A 3, 2. A 3, 3. If I were to remove a row and column, so the first row and the first column. Let's see. Let's do the first row and the second. Sorry, let's do the first column, second row. If I move those 2 rows and columns, then I end up with the submatrix A12, A13, A32, A33. That's a submatrix corresponding to this element here, because that element is in the first column, second row. So I remove its corresponding column and its corresponding row, leaving the submatrix. You may be asking, why would I do that? We'll get to that when we talk about how to calculate the determinants, which occurs next module. Later in this, I think 2 modules from now. Right. That's a submatrix. A permutation matrix is any matrix that permutes the order of some other matrices, rows, or columns. The identity is the trivial permutation that does nothing. Let's see. That would be a different permutation matrix. Note there are 1s in the rows and the columns, but they're moved around. This would permute your rows or columns of the thing it's multiplying. If you don't know what a permutation is, you can go back to the probability, the first lecture on probability, which we talked about permutations and combinations, but all it means is changing the order of something. In this case, changing the order of the rows or the columns. That's a permutation matrix. That occurs much less often than these 2 up here, or this one. Hey, I'm almost done. So that's that. Next, an idempotent matrix is a matrix A such that if you multiply A times itself, you get back A. In other words, it doesn't really go anywhere, right? So if you view A in one of the many ways we talked about it as an operation, as a way of representing a transition between states, well, for an idempotent matrix, if every time you transition, you get back the exact same transition you had at the first place, right? So additional transitions don't take you anywhere, right? The first transition is important. After that, each additional transition doesn't do anything effectively. Not used that commonly, but it's a term you might see, so there you go. For a much more important one, I'm going to write this in blue, because I'm getting punchy. Singular, non-singular. A singular matrix is one whose determinant is 0. This will not make sense to you until we do determinants. A non-singular matrix is one whose determinant is non-zero. The reason they're so important is a singular matrix cannot be inverted. A non-singular matrix can be inverted. Matrix inversion will be important. We'll introduce it later. But we'll have the inverse of a matrix like this. This will have a well-defined meaning as long as the matrix A is non-singular. And we'll find that this thing equals the identity matrix. So it's a way of creating a multiplicative inverse. The same way 1 over A is the multiplicative inverse of A. A inverse, which we read it A inverse, is the multiplicative inverse of the matrix A. It's much more complicated to find than 1 over A, but as long as the matrix is non-singular, it exists, and this will allow us to do many things, like, for instance, solving systems of equations, in some cases, more easily than we could otherwise. So, again, singular has no inverse, non-singular has an inverse. Okay. So that comes up pretty often. Last couple. A block or partition matrix is one in which you can take a big matrix and put it into smaller blocks. So each of these individual blocks is itself a matrix, and the big matrix puts them all together. So if all these little matrices, say, were 2 by 2 and so on, then the big matrix E would be 4 by 4. E would be 4 by 4. You just stack them on top of each other. A block diagonal matrix has stuff off diagonal blocks equal to 0. So these are 0 matrices, and this is another way you would see actually 0 matrices appear practically, is as blocks in a block diagonal matrix. This occurs sometimes in stats when you have certain data arrangements, but not as common. And finally, the last one of these things to do, and I bet now you're really happy this is a video course, so you have this down, and you have to be listening to me just talk. You can pause and think about it for a while. The very last one of these is an orthogonal or an orthonormal matrix. An orthogonal matrix is one that has the columns perpendicular to each other. The identity matrix is an orthogonal matrix. How do you know if the columns are perpendicular? Well, if the dot product is 0, they're perpendicular. Now you see why the dot product comes up again. If the dot product of all the columns is 0, then the matrix is orthogonal. The orthogonal matrices come up sometimes for certain purposes. You don't need these to be 1s for an orthogonal matrix. For instance, this is a kind of cop-out, but it's easy, and it's also orthogonal. An orthonormal matrix is an orthogonal matrix in which the length of all the columns is 1. So this is an orthonormal matrix. This is not orthonormal, but it is orthogonal. And that's the last of the definitions. I guess we could have put a matrix inverse there, but we talked about that briefly, and we'll do that much more later. And it's not just a special kind of matrix, it's an important thing. It's an operation. So there you go. That was an extremely quick overview of lots of different kinds of matrices. But luckily this is a video, so you can go back and rewind and pause and look at different types of matrices, cross-reference the book, and so on. But that's it. These will come up sometimes, not always. In practice, you should learn to feel comfortable with diagonal matrices, square matrices, the identity matrix, and the other stuff comes up much less often. So there you go. That's the end of the overview of matrices. In the next module, we're going to start talking about matrix algebra, how to multiply them, how to add them, and so on. Thank you very much.